Today we're going to look at the electromagnetic spectrum. The electromagnetic spectrum encompasses all of these different waves. Now within this we have different parts that we need to make sure we pay attention to. First of all, let's look at the layers of the atmosphere. Magnetic waves can only penetrate through certain layers. Not all of them actually go all the way to Earth. For example, gamma rays, they cannot go through the ozone layer, which is right here. X-rays cannot either. Only some UV rays can. All of visible light's capable. And then all of radio waves are capable. Only some of infrared and microwaves are capable of going through. So what we have is only visible light, and radio waves are actually capable of going through the atmosphere itself. Now, as we look at all of this, understand that there are two different types of waves. You have a mechanical wave, and then you have an electromagnetic wave. A mechanical wave requires something to travel through. This is a medium, what it requires to travel through. This is like looking at water waves or things like that. Sound waves, they actually require something to move through. Oxygen, materials, like the string, whenever you had the string in the cup, it would actually move through the string whenever you talked into a cup. Now, electromagnetic waves do not. They can travel through empty space. This is how we actually send signals back and forth through radio waves. So what happens with that is you send a signal from Earth, it goes up to a satellite, bounces back down to a different location on Earth, and then that's how you get TV signals or different things like that. That's even how we send text messages and call people on the phone whenever you use your cell phone.
Positions of 19.2 and 28.2 degrees east.
Alright, well, we'll skip that one. I'll go back to it. I'll upload it to a different place. Now, electromagnetic waves. These are waves that are actually going through different parts. Electromagnetic waves have an electric part and a magnetic part. This is called a vector quantity. A vector quantity is something that we're looking at that has a three-dimensional shape. That's these two. Now, on top of being three-dimensional, it also goes in a particular direction along its movement. So it's going somewhere when it's moving through these different waves.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, as I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. You want a demonstration? Oh! Ah! It's so difficult sometimes to get the line back inside. Woo!
Mr. Groove, Mr. Perkins will see you now.
Now, the electromagnetic spectrum is made up of all of the frequencies and wavelengths of actual electromagnetic waves. And it means whenever you say spectrum, we're talking about full range wavelengths here. This encompasses all of these different wavelengths, all the way from gamma to radio waves. That's what full range means. Now, all electromagnetic waves give off energy in the form of radiation, whether it be visible light or heat or something else. It's still energy being emitted from the sun or a source, like right through here. It comes off as solar wind, and it's electromagnetic radiation through electromagnetic waves. Now, a lot of it is blocked by our magnetic poles. We call the magnetosphere and things like that. But some of it still is capable of coming towards us. Now, these electromagnetic waves vary in size. They go all the way from the size of the nucleus of an atom to some as large as mountains and buildings. They're all arranged in the order of frequency and wavelengths. So, whenever you're looking at this, a frequency is how often it peaks. That's kind of the layman term to put it in. A wavelength is the distance from crest to crest. Okay, so whenever we're looking at this, let's first look at what an actual wavelength would be. An actual wavelength is going to be from the peak to the peak. So whenever we're looking at that, let's start off with this little guy right here. From here to here, that's a wavelength. Also, on the other side of the spectrum, from here to here, is a wavelength. So what you see whenever you're doing this is that radio waves have longer wavelengths than gamma rays. These are the shorter wavelength ones. Now, whenever we're looking at frequency, how often it peaks. If I were to put a box here, let me draw a box. Okay, now within this box, if we look at this guy, within this box, we can fit several different wavelengths. Now, if we're at radio waves, it may only go over the shape of one wavelength, you see. But if you go over here to gamma rays, it includes several different little wavelengths that we've got going on. Let me get it back straight. There we go. It actually will include several different wavelengths, and that's what you see here. See all these little peaks back there? That's what we're talking about with a wavelength. Now, whenever you're looking at this, because gamma rays fit more of these peaks than radio waves do, that's what we're talking about whenever we look at frequency. The frequency is how often it actually peaks in a given area. So whenever we're talking about that, we're going to color this guy green. The frequency over here is a lot lower for radio waves and a lot higher for gamma rays. And it all has to do with how many peaks you have in a given area. The more number of peaks, the higher the frequency. The fewer peaks, the lower the frequency. Now, frequency is directly related to actual energy. When we're looking at this, the lower the frequency, the lower the energy will be. The higher the frequency, the higher the energy will be. Now, you'll hear a difference in saying like the electromagnetic spectrum, and then you'll hear us talk about the electromagnetic spectra. Tra is singular, it talks about a particular wave. Is plural. It talks about all of the waves encompassed together. Now, what is on either end of the spectrum? So let's look. Spectrum means the entire thing. And on either end, we have gamma rays and radio waves. That's on either end of the spectrum. Now, if we are looking at visible light, on the other hand, visible light is a little different. On either end of visible light, remember, visible light includes Roy, G, Biv. So that means on either end of visible light, you have violet and you have red. So, red and violet. It's not infrared or ultraviolet. That's actually, those two are not included in the visible light. Colors in the visible light are organized according to high to low frequency and long to short wavelengths. One thing about visible light is this is the only one we can actually see ourselves. The only one we can see. All the others we cannot see naturally. We have to have some form of assistance. So which color has the shortest wavelength? The best way to do this is you look at all of this information over here. And also remember red shift, blue shift. So if a red shift means moving away, because remember this was space, that means the wavelengths are getting bigger. And if a blue shift means coming together, that means the wavelengths are getting closer together. Take that into consideration. So remember, you have your wavelengths right here. You have red, orange, yellow, green, blue, indigo, and violet. Those are your different wavelengths. The one that would have the shortest wavelength, if you compare, this is where they are at, right here. As you move to this direction, my wavelengths are getting shorter, so the one with the shortest would be violet. Then if you think of it this way, here's the wavelength. If you move that direction, it's going to be getting larger. So the one with the largest wavelength will be red. Now, whenever we're talking about locations on the spectrum, the actual image and the picture of the spectrum that you have on your note page, all of them are referring to the frequencies and wavelengths. So anytime you hear the word above, now this needs to be added as a side note on your note page. Above means a higher frequency. Think of it going up. So it's going to be more. Below talks about a lower frequency, so it's going to be going down. It's going to be fewer frequencies. So whenever we're looking at this, above means something, if it's a higher frequency, we're looking at it having more energy, which means smaller wavelengths. If it is a lower frequency, we're looking at it having lower energy, and the lower the energy, the larger the wavelength will be. Now, whenever you're looking at all of this, what is just below visible light? Now, let's go back over what those words actually mean, okay? Remember, below means lower frequency, and above means a higher frequency. Now, on either end of this, you have infrared and ultraviolet. Infra means below. Ultra means above. That relates directly to what we were looking at up here. So just below visible light is infrared. Means kind of in front of the red, lower amount of energy. And above it, a higher energy is ultraviolet. The way I always remembered that was ultra. I always think of like a souped up violet, which means if it's souped up, it's a lot more energy, a lot more going and things like that. So this one's above it, and then the other one's below.
In the last 150 years, scientists and inventors have built on the understanding of the differing wavelengths and frequencies of the electromagnetic spectrum to develop a dizzying array of technologies that have benefited all of us. Radio waves have the lowest frequency in the electromagnetic spectrum. When a radio program is broadcast, an antenna sends out radio waves at a certain frequency, or number of waves per second. Every radio station has its own frequency. When we tune in a station, what we are doing is adjusting our radio to the same frequency of the radio wave broadcast from the station's antenna. When they are both on the same frequency, our radio receives the signal from the station and transforms it into sound waves, which we can hear. Many radio waves can be broadcast at the same time. As long as they are transmitted on different frequencies, none of them will interfere with the others. Television works in much the same way, but the frequencies are higher in the electromagnetic spectrum. An electric signal carrying information about the image arrives at the back of the television tube. Those signals send electrons to the front of the tube, creating dots of light on the screen. Those dots are quickly assembled as an image, which changes so quickly it appears to move and provide action. The curvature of the Earth limits the reception range of telecommunication signals, since electromagnetic waves usually travel in a straight line. In recent years, satellites have been placed in orbit high above Earth to get around this problem. Signals are sent from Earth to the satellite and back to Earth again. In this way, signals can be sent all over the globe. Increasingly, electromagnetic waves with higher frequencies are being used. The signals in cellular phones and telecommunication transmitters are microwaves. The same type of wave is used in microwave ovens. Radar is another use. It was developed in the Second World War to detect incoming enemy airplanes. Microwaves are sent out from a tower. The beams bounce off incoming aircraft, and some of the signal returns to the tower. Instruments read this signal to give the location of the aircraft, its speed, and direction. Today, radar is an essential tool for defense and civil aviation. Infrared rays have been adapted to help people see in the dark. Ultraviolet is used in fluorescent lighting. X-rays are used for dental and medical applications because their short wavelengths can penetrate soft tissue and show bones. The difficulty in using the waves that are higher in the spectrum is that they can be dangerous to humans. Overexposure to X-rays, for example, can lead to serious medical problems. But the more that is learned about electromagnetism, the more applications are found.
Now, as we're looking at all of these, we're going to slowly work our way into looking at all of their functions. This is picking up on the back of your page. So gamma rays. Gamma rays can move through all matter except high density subjects like lead, concrete, different things like that. They have the shortest wavelength and they come with the highest amount of energy. Gamma rays, most gamma rays are not capable of penetrating the ozone layer. Most of them are not. Now, if we keep having problems with holes in the ozone layer, then they will be able to. And remember, the video said the higher the energy, the more damaging effects we'll have. So we've got to really make sure we pay attention and try to save our ozone layer and be environmentally friendly as possible when it comes to gases being emitted and things like that. A gamma ray is a part of the different types of the radiation. So if you look right here, you have three different kinds. You have alpha, beta, and gamma. Gamma is the one that we're looking at right now. There's not three different kinds of gamma. This is just the one that we're looking at. Alpha cannot even go through your hand. That's the weaker electromagnetic waves. Beta can go through your hand, but not through metals. That would be like high power X-rays almost. And then gamma rays can go through your hand, can go through metal or soft metals like aluminum, but they're not capable of going through actual lead. Lead is too dense. The effects of gamma rays. Gamma rays are very damaging to cells. They can actually kill all living cells with excessive exposure. Because they kill all living cells, we are capable of using them. Sorry, hold on just a second. There we go. Because they kill living organisms, we are capable of using them to sterilize medical equipment and water. They kill off all that old bacteria, different things from other humans whenever you go into surgery. They can also kill off bacteria and different things like that in water for fish tanks, which is what's pretty cool. Another good thing is that we can use them for cancer treatment. Since they do kill living cells, we can use them to locally kill particular cells in radiation therapy to help prevent and reduce the size of tumors. So this is an example. What we're looking at is there's a tumor going through different treatment stages, and you can see there's treatment and it starts to get smaller again. It'll grow back a little bit and they treat it and it keeps getting smaller and smaller until it finally goes away. Now let's go into X-rays. X-rays are high energy, high frequency wavelengths. They can travel through soft tissue like skin and muscle, but they're not capable of traveling through bones. Repeated exposure to X-rays can actually damage living cells' DNA. And you see at this image here, you have all of these gaps in DNA that damage that DNA, and now that DNA is not very functional because it has so much damage to it. The way that we use x-rays. We use them in medical imaging, which is an x-ray image. They have security checks, like whenever you walk through those little sensors at the airport or different things like that. And we can use them for small-scale cancer treatment for just smaller sized problems and things like that. The way that all of this works is you have the actual x-ray machine, and it sends wavelengths down, and it'll stop. And whenever it slows down, it'll either slow down or it'll bounce right back. And so it goes and it'll slow down some, and it'll go and it'll bounce right back, go, slow down some, and then you get an image of an arm, and then where it slowed down too much, that could be where the bone's at. So you get an actual image and you're able to see where there's abnormal growth or problems like this. You can actually see what's going on and where everything is at inside the body. Now, one thing about x-ray images, though, is that it only really works by themselves with bones. If you're wanting to look at intestines, you have to have assistance. There's some things you can take, like a barium meal, and what that does is it acts like a tracer, and it'll highlight your intestines where you can actually see the stomach and your actual small and large intestines to see if there's anything wrong or going on that needs to be notified in case you have intestinal tumors or different things like that. Ultraviolet light. Ultraviolet light is probably one of the coolest wavelengths out there. This one is higher energy and frequency than visible light. It's a shorter wavelength than visible light and can make some minerals grow. Remember, ultra, souped up, so higher energy and frequency. What's awesome about all of this is this first picture is what we see rocks as. Certain rocks, you know, the way rocks are compressed together and you have all these different minerals and different things in them, you put them under a black light and the minerals will actually glow or be highlighted like this, just like black lights do to white clothes and different things in your teeth and all of that. The effects of ultraviolet, Ultraviolet, with prolonged exposure, you can cause damage to living cells. The way that it can cause damage, primarily that we have to worry about, is the UVA and UVB sun rays. These are what cause your skin to tan or burn, and excessive burns on your skin from the sun can damage the cells and cause them to malfunction. What happens is it damages the DNA of the cells, just like gamma rays do, and it hurts the cells to know when to make more new cells and when to stop. And so it just continuously keeps making these cells, and that's how you kind of have a development of a tumor or different things on skin cancer. Or that's whenever you start getting problems with, you know, sunspots or development of freckles from being out in the sun for too long. They can damage your retinas. Your retina is the part of your eye that you need to see, and so ultraviolet light, because it can damage living cells, your eyes are made up of cells, if it damages your retinas too bad, that can actually cause blindness, which is why you're always told never to stare into the sun because of ultraviolet wavelengths. Now, on the other end of this, ultraviolet waves are good for us. It helps our body produce vitamin D. Vitamin D is essential to stabilize your mood. Mood stabilization, if you have a vitamin D deficiency, a lot of times that can cause a person to be thrown into depression. And people who live in the Arctic and in places like that, or if people live, say, in Northern Europe or different locations, they'll actually get prescribed ultraviolet lights or different things like this with tanning beds to help replenish that vitamin D in their body. And so this is kind of what we're looking at with UVA and UVB. UVB is not that bad when it comes to what it causes. It just ages the skin, forms a lot of blemishes and freckles. Now UVA, on the other hand, that's the one that you actually have to watch a whole lot for. This is the one that will actually tan your skin, and what it does is it goes down here and hurts this layer. This is the newly forming skin layer. If it damages the newly forming skin, then as it goes up to this top part, it's already damaged, and that causes a lot of problems with furthering, actually dividing the cells through meiosis and things like that to make more skin cells. It'll replicate the damaged cells instead of replicating healthy ones. Now, the uses. We've already talked about some of these uses, like making things glow, sterilization, vitamin D. You need to know that it sterilizes. Vitamin D is a big thing. On top of being able to sterilize medical equipment, it'll also sterilize water safely. That's the key thing, and it can do this at a safe range. And now over here on the picture, this is what we see a flower as. Insects can see it any of these three ways, depending upon the insect. And that allows them to see the actual place where the pollen is, which is what they're needing to. They have this additional ultraviolet range that we don't have over here. It's empty. And so this is with water sterilization. You have the first tank that's full of algae and bacteria and things like that. And you can actually go to PetSmart, Petco, or Pet Palace, locations like that, and find a UV lamp for your fish tank. And after a while of that having that UV radiation, and now it's very low powered, it's not that damaging, but it's enough to clean the water. We even use this type with water sanitation, making sure the water gets filtered through cleanly and well enough to be refiltered back out into public. Now, visible light. Visible light is the only one we can actually see. We can't see any of the others. This includes Roy G. Biv, where the longest wavelength we have is red, and the shortest one we have is violet. It's the only part that we can actually see. And so what happens is the combination of Roy G. Biv is actually white light. That's what this image shows you right here. This is all of Roy G. Biv. And then it goes through a prism, or it can go through a water droplet like in the sky, and it splits it into all the different colors that we have. And that's how we actually get rainbows and different things like that. It's just like whenever you squirt the water hose and you put your finger over the end of it, make it mist. Within the mist, those water droplets in the air, you can see a rainbow. Now, there's nothing really harmful about color. It won't harm you or anything like that. It just enables us to be able to see. The absence of Roy G. Biv, without any of it, is darkness, which is black. So it's just opposite of crayons and things like that. Now, a cool thing about all of this is red light encompasses 90% of a plant's photosynthesis operation. The other 10% is the rest of it, the OG Biv. And now, whenever you have this, if you're looking at the bottom picture, you have your pupil. And then the colored part of your eye is the iris. All of these different colors will go into your eye, including infrared and even some ultraviolet, even though it doesn't say it here. It'll go into your eye to the back of your eye, to these little receptors back here. This is what enables you to see. Now, sometimes These harmful UV rays can get into your eye and cause damage to this part here. That's what happens whenever you walk outside and it's so bright, you naturally squint because it hurts to see. It's because your eye isn't needing to take in this much, and so your iris is trying to adjust, and it's hurting this part of your eye. And so that's why it's always important to make sure you wear sunglasses or have some sort of shade over your eyes, especially down here in the summertime when it gets really bright outside. The way light is emitted. Think of it like molecules. When molecules heat up, they move faster and faster and faster. Now, when electrons do this, they move faster and faster and faster, and then they'll actually move fast enough to where they start emitting heat. It's like whenever you're rubbing your hands together with friction. As they vibrate, sometimes that heat isn't enough. It isn't enough to just emit heat. They have to give off energy in a different form. That's whenever they begin to glow with visible light. It's like whenever you light a log on a fire and it gets glowing hot, or metal that you see where metal workers are putting them in the coals and then bending that metal. It gets red hot because what's happening is those molecules inside of it are moving so fast, heat isn't enough, and it begins to glow. This is where we actually get visible light, where they begin to glow at that point. Now, as we go through, we're getting to infrared, and notice infrared is a longer wavelength, which means it's a lower amount of energy. Infra means below, so it has a longer wavelength than the color red. So it also, since it has a longer wavelength, it has a lower frequency. It comes with a little bit less energy. It travels from the sun to earth as heat. That's the only real key thing about infrared. It's heat. And we can't naturally see this heat. We can feel it whenever you walk outside in the springtime and you feel the heat on your arms and it feels so great because it's nice and warm. You can feel it, but you can't see the heat like right here or in the trunk of this elephant. You can't see it like what you would be able to feel it. The only really harmful thing about infrared waves is that it can lead to heat exhaustion. Heat exhaustion comes from sweating too much and not replenishing your body of that water. And so you dehydrate and you end up having a heat stroke. And you can even see we use infrared with military and hunting, those night cameras and different things like that. Sometimes they'll look like this image, or sometimes they'll be the greener images, just depending upon the type of infrared that's used. And now this shows you the difference in being in the shadow of a tree and outside of a tree on cement or on bricks. In the shadows, it's 102 degrees. Once you step outside of the shadow and you're on the little cobblestone, that's up to 127 degrees. So that's a drastic difference. Some insects will actually use infrared wavelengths, that's how they see, to detect prey, like snakes or things like that. And that's what that bottom image is of the rat. That's how they see it. They see a small body moving and they can determine that. We use these in the night vision goggles. That's where you see the green. Infrared wavelengths are also used in your cell phones to help send signals, TV remotes, other types of remote controls for like little remote control cars and different things like that. Now we're getting to microwaves, not the actual microwave oven, but a microwave itself. A microwave has a shorter wavelength, a higher frequency than radio waves. They have higher energy than radio waves, but they have a lower amount of energy than infrared wavelengths. Now, some microwaves are capable of penetrating through the ozone layer, but not all of them. Usually, we don't have a problem with them. Microwaves. These cause fat molecules to vibrate extremely fast. When this occurs, the more movement, they start to heat up. This is how food is cooked in the microwave oven. Now, the problem with this is we use a lot of microwaves for sending signals back and forth with military personnel and pilots and things like that on planes. The military personnel who drive planes have to actually watch, especially, or even if they don't, if they're dealing with microwaves, they have to watch the amount that they are around these microwaves and monitor that. Otherwise, this could happen to them, and that's an extreme case, but it is possible. So their uses, we use them to cook food in microwaves. We use them in our cell phones to send signals. Microwaves are used in radars to determine different densities of molecules within our weather. So you can they give us different colors, and we can color code to the different densities to see more severe, like over here where it's red, and then less severe where it's green and things like that. We use them to transmit different signals back and forth, and in cell phones. Radio waves. Radio waves have the lowest frequency, the longest wavelength, and the lowest amount of energy. Now, radio waves are split between AM, TV, FM, and some radar. Now, with AM, these are the largest of them. They go from 3 kilometers down to 300 meters. Below that, you have TV wavelengths. And then after that, you actually have FM radio waves, which are about 3 meters. Radio waves, they're given off by stars, transmitters, sparks, and lightning. Lightning gives off radio waves. So whenever lightning strikes, you may hear or see interference, like a glitch in your TV, or you may hear a glitch on the radio, that little fuzzy part. What happens with that is your radio signal's going through a certain frequency. When lightning strikes at that same frequency, and your radio doesn't know which one to pick up. And so what you hear is that sound that it makes for just a split second. Now, larger doses of these radio waves are believed and have somewhat been linked to causing cancer, different types of cancers, leukemia, or other disorders. There are even people who live near power cables and radio towers and things like that claim that it has affected their health, and they can feel the actual energy coming off of these radio waves, even though they are the lowest energy wave that we have. So uses. Again, cell phones use radio waves. We use them to transmit radio and TV signals. We use them on radars. Your AM and FM radio within the radio signals uses them still. And what happens is it goes from the place to this vague internet thing. The internet is satellites and different systems like that. It's not just some cloud up there. It goes to them, to the satellites in that outermost layer or whatever layer that they're in, and then goes back to these receivers, which then send it to the house. This is how we send signals back and forth with the internet. If you're looking at computers and things like that. If you're using a cell phone, it'll go up from the phone, bounce off of a satellite, go to the next person within that split second, and then you're able to talk to them. So within a millisecond, your phone changes sound waves, which are mechanical, to electromagnetic waves to send them into space, bounce off a satellite, come back to the other phone, changes it from electromagnetic waves back to sound waves, all within the matter of just a half a second, if not less. And then finally, we are done. So that is your unit on electromagnetic waves. That way you know what's going on, and if you need any additional help or if you have any additional questions, just write them to the side and I can answer them when I get back or whenever you see me again. Bye, guys.